Then, oh, okay. So can you see the slide, or do you see my side?
No, I see the slides.
Oh, perfect.
Yeah, looking at it.
Wait, are the slides on the left? Okay, let me fix that in the share screen portion. Screen 2. Let's give that a look. Is that better?
Yeah, that's perfect.
Alrighty, and then I change slides. Let's see if it follows. Oh. Fortunately, this is. I have to click down here. Okay, so that changed on your end? Okay. All right, we'll go ahead and get started. And so I'll just start off with a little bit about myself. My name is Jeremy. I'm a senior in aerospace engineering with a minor in manufacturing. And so these are my last few weeks at Purdue. I'm here giving a training on introduction to CAM. I'm a student ambassador for Autodesk. I've been an ambassador for about 2 or so years. I just work helping people with their projects and with software. And so I get to see a lot of really cool use cases and help people get used to Fusion, which is an awesome experience. And so I'll start off with a little bit about Fusion. So Fusion is by nature an end-to-end product development platform, which means you can do pretty much everything. So as opposed to some softwares that are really specialized and they excel in their fields in design or in CAM or in machining and injection molding, this software is focused on a lot of different things, right? So it allows you to work in a cloud-based environment, share your projects with other people, and get everything you need to get done all in one platform really simply. And so that's one of the real big benefits about Fusion. And as we said, it's cloud-based. So you can access it on any computer, Mac or PC, not Linux, sorry, Adriana. And you can do it in a computer lab. You can do it even on the internet or on your phone to a limited extent. And that makes it really great to collaborate and work on your projects. And the focus of today's talk is computer-aided manufacturing, right? So you have your part, you've designed it, you've simulated it, maybe you've made some renderings to get some funding or get some people interested in your project. And now it's your time to make the actual part. And you're going to show up in front of a CNC machine or even a 3D printer, and you have no idea what to do. And so we're going to start off with, okay, what do I do when I'm making that part? And so Fusion has something called CAM, or computer-aided manufacturing, the purpose of which is to go ahead and take a tool path that you come up with on your computer and then send it to the machine. And the machine will then read that machine code, move around, and make your part. And so Fusion will go ahead and take a special code that's internal to the software and translate it to any machine. So you can see lathes are down on the left there, mills on the bottom right. And there's those tool paths that would be correlated with it in the upper right, the upper left. And so just quick basic on that, a lathe turns your part, and then a static tool comes in and removes material. Well, a mill has a spinning tool that moves into a static part. And so with Fusion, and feel free to stop me at any point as we start to get into content if you have questions. Fusion can handle a lot of different things. So listed here are some different types of milling. So we have 2.5 axis or 2.5D milling. Basic idea is I'm making a bunch of flat surface parts at different levels. So I'll move to a different height and then move around and cut, move to another height. We have 3-axis simultaneous milling. So I'm making really curved surfaces. So we're moving up and down as we're moving across the surface. We've got turning. We're making round parts in that bottom left portion. We've got water and laser cutters. That's 2D cutting. So if you're trying to cut a piece of sheet metal out, carbon fiber, something like that. And then we have some more advanced things like probing. We can move a part in 5 axes to get to the different side. That's what we call indexed milling. We can wrap 4th axis. And that's when we're moving that tool path basically around a moving cylinder. And then we have multi-axis milling, which is 5-axis milling that's simultaneous. And all that means is your part's like moving in all these different directions, allows you to get to those surfaces. This isn't the focus of today's presentation. So if you have questions about 5-axis milling, 4-axis milling, 2D milling, and now Fusion has additive and PCB stuff as well, feel free to reach out and my team will get in touch and make sure we can do the best to help you. But we're going to be focusing really on 2.5D milling because that's the foundation of most of the parts you're making. All right, you're going to make a bracket, drill a few holes in it. Maybe you'll do some cool surfacing, and then we can help you with that if need be. But we're going to be focusing on what's in the top left. Any questions on that? I know I dropped a lot of information. All right. So then we've got milling and turning. Some of you may already know this, and I mentioned this. As I said, milling, your tool's turning, turning, your parts turning. And there's tons of different machines that can do this. That router, for instance, is 2D. The lathe is turning. Water jet's 2D. There's tons of different types of mills. This is pretty clear on that. And I'm going to go ahead and keep moving, but I can answer questions on that as well. We're going to get into the basics of the CAM workflow before we open up Fusion and get started hands-on, and that'll be the bulk of tonight's time. So getting into the CAM workflow, the first thing you have is your CAD part. This can be the part you designed in Fusion, but it can also be the part that you brought in from another software solution. So Fusion has something called AnyCAD. It can read CATIA, it can read NX, it can read SolidWorks CAD files. If you import them in, it'll convert them to Fusion 360 geometry. It obviously does not keep the history, so it doesn't know that you made a hole here and then you made this face. It just keeps the 3D geometry. But you can go ahead and take that 3D model and define your job setup. So your job setup is telling that computer where everything is. So you tell it the hunk of material that you start with, which we call your stock. You tell it your final model, this is what I want to end up with, and you define your coordinate system. And your coordinate system is basically just where the machine thinks it's starting from. And when we machine, we have what we call a part zero. And that's something we've probed or defined. We have a way of locating that. And then the commands sent to the machine are then referenced from that point. So you could see maybe that the zero's in the dead center of this part. It could go over and drill a hole an inch to the right of that. If I put the zero in a different spot, that dimension might be different, but it's trying to do the same thing. Does that make sense to everyone about the idea of a zero? And I'll go into that a little bit more when we do the definitions in our demo. We're going to go ahead and define our operations. This is where we tell it what the tool is going to be doing. And so there's different types of operations, and I'll briefly touch on those. We have facing operations. So the tool is moving across the surface, making a flat top to it. All it's doing is a flat surface. There's roughing. We're getting rid of material as fast as possible, but we're not worrying about that final finish on the outside of the part. So it's going to leave rough edges, which is why we follow it up with a finishing pass or a contour. It's going to go slower, but it's going to give us a nice outside finish. And then obviously we can drill and we can chamfer, we can do some other things as well. Does anyone have questions about tool paths briefly as we touched on them? No, all right. And then there's tons of different tools you can use to do that. And we'll talk about those as we go through our demonstration. So the end mill is primarily what we do for a lot of our tool paths. This is going to be somewhat important here because when you open up Fusion 360, you're going to see 3D and 2D tool paths. And the difference is simply how the geometry is defined. So in a 2D tool path, I tell the software, this is what I want to cut. In a 3D tool path, it looks within a given area and says, this is the stuff that has to stay behind, right? So a model-driven 3D tool path looks for the geometry, whereas a selection-driven 2D tool path, I have to grab the edges. So if you tell it to do the wrong thing, for instance, in a 2D tool path, it's going to do the wrong thing. So if you tell the computer to do something, it'll do it, even if it's going to break your part or the machine. So that's just something to be aware of. And we have tons of tool paths. I won't spend too long on this. We've got pockets, adaptives, contours, and I can send you guys these slides because it's a really good visualization of all the tool paths Fusion has. The primary ones you're going to be looking at are contours and adaptives. You see this pocket toolpath, and people try to use this a lot, but the difference between our pocket toolpaths and our adaptive toolpaths is really the efficiency at which we remove material. And so you can see that adaptive toolpath, it's taking a really heavy pass and it's engaging what we call engaging a lot of the tool at once, and that can break your tool. So that adaptive toolpath maintains kind of a constant, what we call step over. And so it keeps that tool nicely loaded. And you'll see that in this next image here. There's a large, like half of the tool is cutting at once, which can break your tool. Adaptive is efficient and uses that same percentage of the tool throughout the cut. And that's just computer generated. And we have our advanced like 3D tool paths. We're not going to focus on these, but you can see that you can get some really cool curvy geometries this way. Any questions on tool paths? Once again, we'll talk more about this in the context of our demo. Am I moving too quickly at all? Sweet. All right. You've got lots of tabs packed with options, and I'm not going to go into detail about this. I'm simply showing you that this exists. The stuff we're spending the most time on is our tool tab our geometry tab, and our heights tab. The rest of this is really for troubleshooting, especially linking. You're basically fine tuning how the software comes into and out of a cut or moves in between. As you get more advanced, you'll begin messing with these more. And if you go, for instance, to a machine shop on campus, like the Bechtel Center, they'll come in and they'll work in some of these tabs when they're fixing your code up. But you may not have the necessary background to work with this, and that's fine. The goal of tonight is to give you an understanding of these toolpaths at a very foundational level so that you can come up with your own CAM, and then you can start to apply that and get more advanced and go work on most any machine shop or any machine around. So as I said, right, we've defined our operations. We can simulate our tool path, which is when we make it, we go through what we call simulation, which is like a 3D interactive like demonstration of what's happening in the machine. You can catch crashes here. Is my tool holder going to hit something? That's the large portion holding the tool. Is my tool going to break? Is my vise, which holds my part, going to get hit? And you can just make sure that everything looks good for that. And then the last step would be to post your code. We translate to machine code, we send it to the machine, and then we run our part. That was a really rapid zip through the details of CAM. And that was just to give an overview. Yep.
All machines run on the same code.
So there are different post processors for different machines. So some codes, some machines have different controllers and their own proprietary commands. So one machine might have a command that's different to turn on coolant or to spin up the spindle. And so we have what we call a different post processor. And so Fusion has a library of these post processors, and they just translate it, same computer code, they translate it to the different machine codes. So usually if you're on a machine, that'll be provided to you or your company will have it. The Bechtel Center has their own. So sweet. Any other questions? Alrighty. So now we get to the demonstration portion of this. Does everyone have Fusion installed? Does anyone not have Fusion installed? All right. So if you guys want to open up Fusion, we're going to be using some default content because I want you all to be able to access this and also know where to find resources. And we'll slow down here because I want to be able to answer questions as we go, solve problems as we go. I'm going to minimize that there. So everyone is here. All right. So we're sitting in our Fusion workspace. I'm going to go to my individual team. And I'm at my home page. So I've got a lot of my different projects. I have a bunch of different things sitting around, but I do want to be ready to work in most workspaces and with a lot of different assets that we call them. So I'm going to go into my settings, and you all should do the same. In preferences, we're just going to change a few things to make sure we're ready to go. Just in general, we're going to go into manufacture. And so if you're all with me on that, there's a button called Enable Cloud Libraries. I want you to make sure that that is checked. What that does is that just makes sure that if you save tools, you save post processors in your what we call cloud library, where your assets are, that's accessible to you. So has everyone done that? Does anyone have any trouble with that? We need more time for that. All right. Go find units really quick. You can change your default units for anything. I'm going to change my design units to inches. You don't have to do that. The key is change your default manufacturing units to inches. In the United States, we do a lot of our manufacturing in inches. The machines are set to that. The cool thing about Fusion, you can design in metric if you need to, and your manufacturing workspace can be separately in inches. You can change that for individual parts, but we're going to be working in inches today. And then just a fun little tip is if you want to see some cool features that are in testing, there's a ton of cool testing features in preview that allows you to see those. So if you have a Purdue email, a lot more of those will open up to you. But does everyone have their cloud libraries and their units set for manufacturing? All right, anyone else need some more time for that? Sweet. So if we go to our left side tab, we're going to see a samples section. And there's tons of demonstrations about a lot of features that Fusion has. So you can see circuit board demonstrations, simulation demonstrations, generative design simulations. But the one we're going to be going into is probably going to be our CAM samples one right here. So if you're all CAM samples, you'll see all of the different demonstrations that are available. There are finished demonstrations and there's unfinished like starter demonstration files. We're going to scroll down until we find, let's see if I can grab it. Let's go into, oh, where did I put it? There should be a, hold with me real quick while I go track that down. It may be buried in a different folder. Maybe under basic training. Nope, it won't be. No, I think it should be in that CAM samples one there. Okay, here we go. It should be under tutorials. Here we go. We're going to be doing our 2D adaptive milling tutorial. There's a complete version as well. So if you open up your 2D adaptive milling tutorial, it's under CAM samples and tutorials. You're going to see a part. And I'm just here for the part. This is kind of what I'm working off of. And the reason I'm doing this is because I want you all to be able to access this and access it on your own computers. I don't want to hand around a flash drive. You'll see there's a big lock at the top. That just means that I can't edit this because it's not mine. And in fact, no one in the world can edit this except the Autodesk folks. So we're going to have to save this somewhere that we can work with it. So if we go to our file, we can save as. If you're all following along with me, in the upper left near those boxes, you'll see a file, a drop down. And we're going to go to save as, and then we're going to click save as. Pick a location for it in your own Fusion folders. You may need to make your own new project. You can always move it later, and you're going to hit that save button. And what's going to happen is I've made a version of it that's on my own personal project. So we can go ahead and start working on this part. And before we do that, has everyone managed to get it saved to their own personal files? And if you need help, and me or Adriana will be happy to assist you. But if we're good there, we'll go ahead and get started with the rest of it. So we're sitting in the design workspace. This is where you may be when you start any project. We're going to go to the upper left where we see our drop down. We're going to go to our manufacturing section. And so you'll see right there, it's the manufacturing workspace. If you pause and take a deep breath, you'll see all the awesome things you can work in: generative design, rendering, simulation, drawings. Fusion can do all of this, but today we're going to be in manufacturing. So if you drop in, you'll see your workspace changes. For some reason, my default units didn't change, and that's not a problem if yours are not changed as well. If you click on that edit button, you can change the units to be inches. And physically, nothing changed. It's just displaying everything in units that are in inches. Has everyone managed to get their units swapped over to inches? Sweet. I'm going to save it as I go. And you'll see that there's nothing on the left side except my models and an empty portion called setups. So we talked about creating our job, creating our setup. Fusion's changed the name of that over time. But if we click setup in this upper left portion, we can create our setup. If everyone wants to click that, you'll see a big orange box shows up encapsulating everything. We don't want that. We just want to be working with our main geometry, but we'll get to that. You can select a machine. We won't be doing that, but if you have a preset machine configuration, the software can keep an eye out for bad things that might happen. We're going to be doing milling. So under setup, you can change the operation type if it's different. You see cutting and additive there as well. We'll come back to our orientation in a second. We're going to define our model. This is where we select the physical part we want to end up with. So when I click model, you'll see it's highlighted in blue. I can go over and click the physical body, or I can go over and click the component under the left side, the body on the left side, right? So I could go to here on the left on my tree, or I can go to my body here. We're going to go to my body here. It's just easier. You'll see that the orange material shrunk away. I want to define my fixture in this case. We may or may not have more details in an actual model. Bechtel Center has a full table for the machine, but all I'm doing is selecting the stuff that I want to know if I hit. That way it can warn me if I'm going to crash. We don't want to hit these jaws. We're going to define our stock next. Our stock is our work material. So you can see there's an orange box around this part. I can pick a solid to be my stock that I've made, and then just select anything, or I can define a geometry based upon dimensions. So I want to make a fixed size box, and I actually want it to be something like the width of these jaws here, because I'm not sure about what those widths are. I'm going to go ahead and measure them. You can pause. You don't have to back out of your setup, but if you'd like to, you can. We'll inspect between these faces here. It's 1.95 inches. And then the distance from the bottom I had is 0.165. So that's just going to tell me how I'm going to set up my stock. So 1.95 inches wide in X, or sorry, in Y. And you'll see that this isn't correct yet. It was 0.185, 0.65. And then we'll see that my height, I'm going to make it like 4 inches for now. All right, so this looks absurd. It's really confusing. It doesn't fit the part that we're working with. That width I defined isn't in the right spot. Well, what happened was my orientation was wrong. So you can see Z is pointing off to the left. On my machine, the Z-axis needs to come up out of the top. So if I edit my setup and go to orientation, I can select Z-axis or plane and X-axis. I want my Z-axis to be the top, my X-axis to be left to right on these jaws, and that works too. And so if I hit OK, you'll now see that I have X going to the left, Y going towards me. And if I don't want it to be that way, I can flip the X-axis, and I will. And now our definition is correct. And I can change my height to be more reasonable, right? Maybe we only want 1 inches of stock, or in our case, maybe like 0.75. And that's more reasonable. But we've defined our block of material. So to recap, we went ahead and selected our body. We changed our orientation, selected our fixturing. We defined our stock size. Does anyone have any questions? How's everyone doing with their models? I'll pause. If anyone needs help with getting their orientation fixed or anything else, just raise a hand. Yeah. Yeah, for sure. I'll go through that again. And then if it's still giving you trouble, we'll send someone over to help you out. So
If you want, if you, there's, you can do it this way, which only can do like you can also change the orientation. There's a drop down.
yeah, so for now, we're just going to be changing it in here in case you had a different one, but you can change the model. So all I did was go from model orientation here. I'm going to change model orientation to select Z-axis and Y plane. And I'm defining my Z-axis as the, or the plane as the plane where the axis is going to be coming perpendicular out of it, in which case it's any top face that's flat. And then I want my X going left to right. So I'll pick a line that goes left to right, and I'm going to flip it so that it's going in the direction that I want. In this case, I'd like the curved face towards me for no particular reason. That's what I want. It is the orientation of the machine. Adriana corrected me there. So did that make sense for that setup? All right, everyone got their model set up? Hands if you don't. Sweet. So my software now knows where the stock is, the material. It's kind of thin on this left right side, so I'll thicken it up a little bit. I can just change that X to be 4 inches or 3.5. And so if anyone's wondering what the dimensions are, X is going to be 3.5, Y is going to be 1.95. Z is going to be 0.75. And my offset on here tells me where is my part sitting within this block. We're going to offset from the bottom by 0.165, just because I know that's the distance from the jaw to the bottom of the part. That's somewhat arbitrary. As long as you end up with something that has an orange box with extra space around it for today, it'll be okay. So don't worry too much about that. But it's going to be 0.165 from bottom. And then if that doesn't match, don't worry. As long as you don't have your gray box out, your gray part outside of your orange box. Alrighty, we good to keep going? Sweet. So we've defined our 0. And this is where we're going to probe off of in the machine. So this is what's going to tell the machine where to start from. We can change that if we'd like to. For now, we'll leave it in the middle. The first thing we're going to do is a facing operation. We want to get a flat face on the top. So to do that, here, let me just grab a facing operation. That's going to be in the top left under 2D. It's going to say face. So if you'd like to click that, if you can see that. Everything has a really nice description of what's happening with a image. We'll click it and we'll see a lot of stuff here. Don't worry, it's overwhelming. We'll slowly go through it. We're going to go to our tool. I have a lot more tools available than you guys do, so don't worry about that. We're going to be working out of the Fusion 360 library. So if I go to select tool, we'll go to Fusion 360 library. These values for feeds and speeds are not correct. These are just general starting values. Feed and speed is basically how fast am I spinning, how fast am I cutting the material. We're not going to worry too much about that. But I'll pause here for a second. Once we get through the facing, we'll pause here till everyone gets their toolpath running. So we're going to select a sample tool in inch. My type is going to be what's called a face mill. Oh, I guess we don't have any face mills here as examples. We'll get a flat end mill. And we're going to go ahead and grab a 1-inch end mill for this example. That's really large. We'll choose a finishing feed and speed. Once again, these aren't correct as much. But it's just an example. A 1/2-inch end mill would be more reasonable. So maybe we grab a 1/2-inch end mill. You can choose whatever tool you want in this case, and don't worry about the feeds and speeds. Just pick a tool that's an end mill. And then under geometry, for a facing operation, we don't have to select anything. It gets your largest, highest location and cuts down to it. Under heights, this simply tells it where to go for safety. By default, we usually like to set our clearance and retracts heights to a 1/2 inch away. But that's not a big deal. The bottom is going to be the model top. If I want to face lower, I just lower that dimension, but I don't want to. I want it to cut to that height. And under passes, these details aren't as important, but the step over is somewhat important. On a facing operation, you can use 2/3 of the tool diameter. So you can either go 2 divided by 3, right, times 0.5, and it'll give you an answer. Or you can edit this to make it an expression. So if I right click on this box, I can say 2/3 times, and now I have access to a variable. It's called tool underscore flute length. And I'll go back through this when people catch up here in a second. But now that I've defined that, no matter what my tool is, it's going to make it 2/3 step over. That's how far is my tool cutting left to right on each cut. Multiple depths. I'm not comfortable going more than 0.05 inches down at a time. I know I have more than that left on top, so I'll change that. And then I don't need to touch linking. So if I hit OK, my toolpath is going to generate. Something happened there. Let me see what's up with that. Did I say flute length? I might have needed to say, sorry, tool underscore, sorry, diameter, not flute length. That's my bad. So it's 2/3 of tool diameter. And we'll go back through this after I'm done here. And you'll see there's 2 passes needed to get rid of the material. And it's going to take 2/3 step over each time. So I'm going to pause for a second. I'll let you work on that. And I'll come back through and I'll go back through it here in a second. But let me know if you guys have questions, raise your hand.
Just the basic.
Yeah.
And so all we're doing today.
Yeah, I just thought it out. It's in. Oh, it wasn't there. It was tutorial.
Okay, well, that's good. So I discovered there's another tool that we can use, and that's a face mill.
I didn't know where it was. And so to demonstrate, you can leave it with any tool you want here. You can leave it with the end mill. I can just go ahead and change to a tutorial inch. And there's a 2-inch face mill under tutorial inch. If I select it, we'll see my step over automatically changed to 2/3 because I had the expression. And that's what the expression is there, 2/3 tool underscore diameter. When I hit OK, it takes a lot less time because it's a lot more efficient of a tool. So you can do that as well if you're curious, but you're fine where you are. Does everyone have, how's everyone doing with the tool path? Yeah, I'll come over and help.
Oh, so you launched your tool path?
Everyone got something coming along there?
Oh, so yours is upside down. It's 0 already. Right, so that- And for X, right? Yep. Sweet, and that's the multiple depth section. I'm very over. So go here to the pass. Go to passes. Go to 0.05. as I said before, right, if you tell it to do the wrong thing, it'll do the wrong thing. I've broken stuff because I put a 0 or decimal in the wrong place. It's just the way you learn. It's not an issue. But your tool path is completely valid. But you want it to match mine, that's the way to go about it. I'll go back to it. Someone else had that issue, so I'll go right back through it if you want to follow along there.
Just a reminder, if anyone has issues with those double lines, like they don't see both of these cuts, under our passes tab, if you see where that is on your screen, in the second to last tab, there's an option called multiple depths. 0.05 is what you want to set that to. That just means like if you get a really big chunk of material above it, it takes several cuts to get down to the right depth because it can't handle all of it at once in most machines.
So if you change that multiple depth to 0.05. All right, so the next thing we're gonna do is an adaptive. Is everyone have a good enough facing pass? Sweet, you guys are good over there? All righty, so if I'm gonna do something real quick for fun, this is how we check our work. I'm going to simulate it. So if I see this little thing up here in actions, it says simulate, or I may need to click down and simulate. It allows me to see what's happening. I'm going to put this into the mode you'll see. Oh, that went quickly, but you can see it's really just showing me what the tool and the part are going to do. And there's the tool cutting away. And there's my final face. And then there's that's the final part there. If you don't see your stock, you'll need to click the button that says stock on the right tab. And now you got your block. So, and that allows us to check our work as we go. Next thing we're going to do is our roughing. So our job is to get rid of almost all of the material. And so if we go up to the top, we're going to be working in 2D today. There's a 3D section that does adaptive clearing. It's just a fancier computer-driven version. This is going to let us choose for 2D adaptive. So I've clicked that, and now I'm in my workspace again. I'm going to have you all not touch the controls for a second as I go through something. Your tool you're going to choose for this is going to be driven by your geometry. So I can't fit a tool that's actually smaller than the radius in that corner. So if I have a corner and I try to cut it with a tool that has a radius that's larger than it, I end up with this. I end up with bare material that I can't reach. And so it's always a bad idea also to have a corner that's the same diameter as your tool, because then you're going to load up that tool really heavily, right? So I'm putting 3/4 of my tool into a corner, and that's really not great. So I like to pick a tool that's a little bit smaller so I have room to work. And so that way, when I cut my corner, I'm really only engaging with a really small portion of the tool at once. And so when I pick my tool for this roughing and finishing process, I'm very conscious of the inside corners that are here. If I inspect that corner, my radius or my diameter is 0.38. So I'm going to choose a tool that is less than 0.38, right? And that's because I want my tool to be able to cut the corner. Does that make sense to everyone? Sweet. So if you choose a tool and it doesn't cut everything, that's going to be why. So when I go into my selection window, I'm going to have you all do the same. Tool select. We can go to the tutorial inch section and track down a 3/8 end mill. I don't see one. So I'm going to go to the sample tools inch section. Sample tools inch, sorry. Flat end mill on the right, and find my 3/8 flat end mill and hit select. Does everyone see what I did there? We're going to sample tools. We're going to go to filters, flat end mill. We're going to grab our 3/8 end mill. And when I select it, everything populates, and that'll fit into those corners. Geometry is the next tab to the right. This is where we tell it where I want it to cut. So I'm going to grab my pockets. I'm just going to click the bottoms of all of these places here. But I can also save some time. I can get the outside as well. So if I hit this outside bottom edge, it's going to select everything there. So you'll see that there's blue around the outside, and that's where it's going to cut. As I said before, if you tell it to do the wrong thing, it'll do the wrong thing. So if I reverse this here, it's going to try to cut inside all of this bottom area in blue. We don't want that. So you may have to click that arrow to make sure it's cutting on the right side. So if you simulate it and it messes up, you may have to do that. Our heights, we'll leave it default. Passes, the optimal load is usually 10 to 5% of the tool diameter. So once again, if I right-click the optimal load and hit edit expression, the tool step over, I'm going to replace that with 0.1 times tool underscore diameter. And that's just telling it, this is about how much I want you to cut at a time. Multiple depths, we're not going to do, but if you wanted to, you could change it to 0.9 of the flute length, but that's okay. Now here's stock to leave, and we're going to talk about stock to leave briefly. I mentioned that this toolpath leaves a really weird outer finish because it's really computer optimized. Those, what we call trachoidal milling, that really spirally pattern, leaves weird divots on the walls. So we leave material behind for a really nice finishing pass. And that's going to be 0.02 inches on the outside walls. But on the bottom axial, we don't need to leave anything because it's just the flat bottom of a tool moving against a flat surface. So no matter where it goes, it's creating a flat bottom. And so I'm going to leave that at 0. When I hit OK, my tool path is going to generate. Alrighty, and there it is. Unfortunately, it's going to try to cut through the middle, right? So I mentioned earlier, if you tell it to do something, it'll try and do the wrong thing. So you see that there's this gray portion missing from the middle. What it looked at was that bottom contour and it said, oh, there's no edge there. I'm going to go further in. To fix this, I need to change my selection. We're going to do the outside in a separate one that doesn't have this issue. So I can remove this by clicking it and clicking trash, delete current contour. We'll just start with the inside, right? And then we'll come back to the outside and I'll explain what we'll do there to be tricky. We're going to cheat a little bit. So anyways, has everyone got an adaptive toolpath that's just doing those inside pockets? Raise your hand if you need help with that, or you need some time, and we'll give you that time. Sweet. So. Awesome. All right, we're going to finish that and we're going to do a contour. And the cheating way to do this is to right click adaptive and say create derived operation. So you all see my window there. You're going to right click adaptive, or sorry, the toolpath, go to create derived operation, 2D milling. We're going to select 2D contour. I'm going to leave this up for a second so you all can follow that. And as soon as I hit click on the 2D contour, I'll just hit OK. And what this has done is selected everything again. And if you were to go to geometry, you'd see it selected. But it's kept all the settings the same. And so it's basically just saying, use the same tool, use the same everything, and here's your finishing tool path. And that's a really cool way to go quickly. So does everyone have those two tool paths you were talking about? Alrighty. We're going to move on to the outside. Here's where that selection becomes an issue. So I talked about my problem with it not getting that bottom edge correct, right? See that dip in the middle isn't doing what I want it to do. So that outside actually has the same contour as the top edge. So I'm going to select this top edge. But if I hit OK, it'll just try to cut at that level. It's not cutting lower. So I'm going to force it to go down to the bottom level and use that edge. This is why we kind of have to play to get it to do what we want sometimes. So I'm going to change my bottom height from selected contours to selection and select that bottom edge. And now there's the bottom selected. And when I hit OK, the outside toolpath is going to generate to select the correct height. I'll change my rest machining. like we did before, or sorry, that stock to leave to be 0.02 and 0. And then I'm going to right click, create derived operation, just like we did last time, to cheat and make that finishing pass for the outside. And now I have my finished cam for this side of the part. Well, that's a fun corner. We'll talk about that in a second. So now we have our outside done. And then we'll add some drilling operations, and that'll get us to the bulk of the content before 7:30. And then I'll go ahead and touch on some of the final cleanup that we want to do to make things usable. But while people are working there, I'll pull up the selection we did for adaptive for that bottom height, right? So we're going to be in heights, bottom height from selection, and we're just going to click the bottom edge. So. Everyone doing well on that so far? All right. So now that that's done, we'll go ahead and drill. So I have some holes I need to drill here. I'm going to sneak over to the design side. You can stay where you are. I'm going to sneak and look at the design intent for this. I'm going to see that it's a 632 hole. I'm just going to go ahead and make it something close to that. When you have a good tool library, that's your usable tool library, or you make your own tools. For instance, if you use the Fusion or the Bechtel tool library, they'll have the proper drills and all that. Hopefully they'll have the right ones here, but we're going to create a drilling tool path. So drilling tool paths, all they're based upon is your whole center line and depth. It doesn't pick the right drill for you. You have to select the right drill. So if I go into tool, I'll go to tutorial and see if they have it, but we may be in sample drills. That's not the right stuff. So we'll go ahead and go to, they don't have the drills here. They're all tabs. We'll go to sample tools inch. We're going to go to drill. And I'm going to cheat and Google on my phone what a 632 tap drill is. Yeah, I know we don't memorize our tap drill tables. So supposedly a 632 tap drill is, we find it, a 36 size drill. So I want to find 36. So I'm just going to search 36 in the top, and it's going to pop up with this 36 drill, 0.1065. Exactly. So the tap's going to cut away material to make the threads. So we're not going to do any of of that ahead of time, right? And so geometry wise, I'm going to click my hole. And I'm going to get that top portion too, because I want it to cut there too. You'll notice that the hole has a flat bottom and the drill has a pointy tip. And we run into the issue where our hole can either be, the depth can either be the tip of the drill, or it can be the edge of the drill, right? And so, oh, that's a bad pen. Get rid of my old drawing and I'll draw a new one. We have the edges here of the hole. We have two options for life. We can go with a drill tip through bottom, right? So the edge of our hole is defined by the edge of the drill right there, or the edge of the hole is defined by the tip being at the bottom of the hole. When you design stuff, keep this in mind, right? Quick design for manufacturability thought. No one's drilling with flat bottom drills. Very rarely they are, they exist. So we'll go ahead and put the tip to the bottom there. So you're just going to lose a little bit of extra material. So if you have to worry about breakthrough, That's something to be worried about. But anyways, we have our hole. I'm gonna hit select same diameter. It's gonna get all 4 of them for me automatically. Heights, there's a button called drill tip through bottom, and I'll click that. And now the bottom of the drill is going to the past the bottom of the hole. I'm just gonna hit OK. Well, do it. We could do a chip breaking tap, but this isn't the proper drilling cycle for like an in-depth. This is your type of tool. This is a quick and dirty. It's drilling. Normally, we center it with a special tool called a center drill, and then we come in and we peck drill. These are just fancy ways of making sure we don't break stuff. I'm showing you the basics of how to make the tool path. If you go work with someone in a machine shop, they'll help you get started on the rest of it. So we just have a defined tool path there. Does everyone have that drilling operation functional? Sweet. I chose a number 36. So if you go to your tool library and you search 36, and so the fun thing about Fusion is if I select a 1-inch drill, it is going to drill with a 1-inch drill. And so if you choose the wrong size drill, it'll do the wrong size thing for you. But it's a benefit because you can also alter it later. So say I have a 1/4-inch hole and I want to drill bigger. In my software, I can just tell it to use a bigger drill and it'll over drill. We're going to tap now, which is the same process as drilling, except we'll go to select our tool and we're just going to go to taps ISO. Nope, ANSI, sorry. All the ASME kids are like laughing at me now because I don't have a good fundamental of my standards. We were what, 632? So if I select that 632 ANSI tap, it'll auto select everything there. I'm gonna grab that whole face there. And then if I just hit OK here, we'd run into a problem. So I'll talk about that for a second, but it's automatically generating your toolpath for tapping. You'll see there's a flat bottom. That's because the taps have a flat bottom. But we talked about the tip of the drill. Now we're going to talk about the clearance needed for a tap. So on a tap, you're cutting threads and you're making chips. If you go to the bottom of even a pointy hole, for instance, you're going to mash some chips into the bottom and you're going to jam the tap and it's going to break. So we're going to leave like 10 thousandths of an inch, 15 thousandths of an inch of space, so that we don't have to worry about breaking the tap. So when you design a part, it's not easy for people to tap to the entire depth of your hole. So as a design engineer, keep in mind, maybe I'm gonna leave that hole deeper and the threads will go the whole length in my design, but they're actually just gonna tap maybe here. And so we'll leave 0.15 there, or 0.15. Maybe we'll make it 0.05, something, not nothing. We don't want it mashing against the bottom. So I can do that in the heights portion. If I go to the whole bottom section, bottom height, and say 0.05, there's our offset. And if I look at the two next to each other, you'll see we've got some space. Select all, yeah, same diameter. Did I not do that? Oh, I did. Okay, sweet. So you want to select same diameter. And now we've got that first operation done. There's a few things that are wrong. So if you have to run, feel free. And I'll leave this open to questions in a second. You'll notice that I made a big mistake. I left some material here. That's my fault. I can hit that with a 2D adaptive if I want to, and just select a smaller tool for my corner here, because these radii are just really tiny. It's close to, oh, well, it's 0.11. So I would need a really small end mill to do that. So I'm going to cheat and just ignore it. I'm not going to mess with it. What's up? From a manufacturing perspective, it's more efficient to use a larger tool. So I'm not going in depth. There's ways to do something called rest machining. The software is going to look at what's already been cut and not try to cut it again. And I can demonstrate that really quickly with 3D adaptives.
But the basic idea is the bigger your tool, the faster you're moving material. Maybe you'll want to hit that with a finishing pass. There's ways to just tell it to only cut that area, but they're a little more in depth where you got to start messing with your settings and forcing it to do what you want. But the basic idea of a 3D adaptive, you'll see how quick a 3D adaptive is. We're going to use the same tool for our 3D adaptive. And we'll just say flat area detection on. We'll put that in our correct setup. We'll put our facing operation in front of it. And I'm going quick. This isn't for you to follow. This is just to do it quick. There's a rest machining thing which sees what it's done already. I want you to see the difference between some of these tool paths. And you'll see that this tool path went ahead and just started cutting everything for me. I had to do no work. It just popped out with a tool path. I didn't have to select anything. 3D adaptive, right? Brings with it its own challenges. Now you'll see that these areas here are a problem. So if I duplicate this tool path and I change my tool with the rest machining option on, Fusion will know what to do, hopefully. So if we go to tutorial inch, I'm gonna grab a 1/4 inch end mill. Actually, I may need to even grab a 3/16. That was a 1/16 of an inch radius? Right, diameter. I'm gonna do a 1/4 inch. We'll leave the extra material. My flute length is not that long, but this should still work, right? Flute length is how much I can cut with at a time. You'll see it's just gonna go back and it's gonna hit those corners for me, and that's all. So it found some stupid area here where it thinks I didn't cut. So be it. Oh, it redid everything. Let's see if I can fix it. Ready? We'll go to here. Rest machining. Ooh, from previous operations. Well, it should theoretically not try to cut the same thing twice. If for some reason it's not. So it thinks that I didn't do something. Yeah, so it's not for some reason remembering that I've already done that. So we'll pretend like this isn't happening. But if you do use a 3D toolpath, it should be able to look for what you've already done and ignore it. There's some glitch with its dimensions right now where it's not liking that. But if I do go ahead and pick a smaller tool, you'll see that it's just going to take a lot longer to do it. Yeah, it's possible that they break, and that's a problem. So while this might be able to get most of those corners, it's just going to take longer to do so. So yeah, I can get more of it, but so that's kind of the gist of that. That's why I didn't do adaptives, right? It's because 3D adaptives, sorry, because 3D adaptives are a little more complex and they don't always do what you want. They can do what you don't want. So I've scrapped parts because of 3D adaptives before. You just got to be very in tune with what they're doing. And so if we look at this toolpath here and we ignore this second one that I was messing with, we simulate that, we'll see that we have everything we need to make a part, right? As a design engineer, you won't put these really tiny radii in the corners because you'll know that it'll make me sad. And you don't want to make me sad. It will also drive up your part cost, increase your scrap rate. Lots of other things can happen when you make really complex features, right? So keep it simple. Do what you need to do to make the part functional. And I'm the manufacturing lead on a team on campus. And what I do for that is I make sure that I ask my design engineers, hey, does this need to be here? Can we do this a different way? And if their answer is no, I'll work hard to make it happen. But also, I like to know that they have a reason for everything they're doing because it means they're designing good parts that have manufacturability, that they're doable. And so oftentimes things will need to be a certain way, and I understand that. But at the same time, you want to make sure that
your cost is driven down, and that you're not making people's lives painful. So under geometry, I forgot to select same diameter for the taps, but that's the, Ari reminded me of that earlier. So what's up?
So right now, the way it runs, it cuts everything, except the way the actual, part has a, how we should go about it.
Yeah, flip it over and hold it in a vise, right? So I'll go ahead and do a demo here. It's gonna be the same exact thing you guys did before, right? So here's what I'll do for it. I'm gonna hide these jaws. And this is why I'm not doing too much on this. It's a second operation. The Bechtel Center will make you make a whole new file for it. In the olden days, we just hoped things didn't hit and we did it this way.
In the olden days, you didn't make it set up, you flipped it over, and you did it all in computational programming.
Yeah, and so there's a way to say, here's it, steal it from the previous setup, right? We'll use this 0. I'll hold it like this in the machine. Can anyone guess what the first thing I'm going to do for this block once I flip it over is? 0, right? And then the first tool path I'm going to use to cut is going to be face. And then I'll get rid of the weird geometry in the center with a adaptive, right? And I'll finish it with, someone said it, contour. Yes. So it's the same 3 things for all these geometries, right? It's somewhat simple, but the big secret is like, okay, I've got a complex part. I just have to do this like 5-10 times for some weird features.
So there's no way to just do it all over.
Flip it over. Yeah, so there's fancy ways of getting rid of it with a 5-axis machine. Like sometimes you can flip it sideways and go back and forth on the back side of it. It doesn't work well. You'll have to flip it over. So I'll face and I'll do that real quick, right? In fact, I'm just going to copy paste the old stuff from here. My facing stuff will generate automatically in the correct orientation. My adaptive, I'm going to grab this corner here and I'm just going to do a create derive on that contour. And then I have the backside done. It should theoretically carry over the stuff that I did before, but if we remember last time, I already got rid of all of this old material on this side here. So it's now faced flat and there is now a notch in that bottom side that's good to work with. So.
If you had like a part or something that had like a internal path, because that's not like a linear path, would you be able to machine that?
No, so if that's a 3D printing issue. So you're talking about like a fluid channel
Yeah.
that's curving. Yeah, okay. So you'll want to 3D print that, or you can sometimes have intersecting drill holes. So if I drill this way and drill that way, they'll hit each other, but that gets me 2 angles and that's it. So those are 3D printed parts and they're beyond the realm of traditional machining. Sometimes people will print it and finish machine it. And then that's where you get into the world of all these cool rocket engines where they'll print the whole engine with channels deep inside to cool, and then we'll chuck it into a machine to make it flat and make it usable. And so, yeah, so there's some really advanced stuff you can do.
Just one other question. Do you have any other like great advice for like design engineers who are working in like just to make manufacturing easier?
Yeah, so I think I'll just give a perspective on in the manufacturing world. When you design a part or you come on as a design engineer, you're often responsible for that part through its entire life cycle. That means that it's your responsibility to sign off on non-conforming hardware. So the tighter you make a tolerance, right, and you'll learn about tolerances as you enter the workforce. I'm sad that they don't teach GD&T, which is a way of telling it, okay, I have this much I can go in each direction safely for a part dimension. But you'll have to sign off on hardware that's out of tolerance. And so if there's $1.2 million of parts sitting on a shelf that are possibly usable, the company is going to have you go through and check, does this part actually function even though it's outside of what's allowed? And so when you make a tolerance tight or you make a part more difficult than it has to be, that's the manufacturability side of things. So doing that, learning how manufacturing works is a great way to design good parts. And then even getting hands-on experience is a cool skill to have. And so not making things more complex than they have to be, thinking of lots of these different things is, I guess, just my general tip to anyone who's a design engineer, right? And so I have the education as an aerospace engineer. I've got the hands-on experience and learning that I've done on my own here on campus that's been really fun for me. And so I think you'll outshine a lot of the other design engineers if you kind of have a perspective on just what does manufacturing look like, and if you're designing parts that can be made, that puts you ahead of a lot of other people, right? Because they don't have to come back and say that this cannot be made, and then someone's going to send back the part and say, oh, we're not going to make this, or they're going to quote you like $1 million when it really costs $100,000 or something like that. So I think that's my big tip on that is the more you learn about manufacturing, you don't have to learn about the details and how to do all this, right? But for instance, you learned today that your corner size is really going to define your tool size. So the smaller I make a corner, the more difficult things have to be. I can't machine a sharp 90-degree corner on the inside, stuff like that. So, yeah.
So, we added clearance for like the grips and holes, but it starts out as like a solid like block.
Yes.
So how do you get it to like slice off that block basically at the end, right?
What do you mean?
So
Yeah.
when you start with it,
So we're here with our big solid block.
yeah, you're with the big solid block, but you want this piece to be like separated by this line all the way to the bottom.
Mhm.
So can you like slice? How do you slice? through
Oh,
that?
that's the facing operation we do on the backside.
On the lathe, it would be its own thing. You're right, on the lathe. it would
So
be
so,
the
you would, so even if there wasn't that cut in the middle there,
Oh, so yeah.
you would still have to turn it over.
So if there was no cut in the middle, my tool path would simply just be this on the backside. And oftentimes I'll have a really complex part that I just chuck in upside down and just run a facing pass along the backside, right? And I have to do that for every part I make. There's not really a way to avoid that. So, yeah. Sweet. Yeah, I program it. I don't do it by hand. That's long. Any further questions? Hopefully my insight's useful. You guys got a taste of CAM. Once again, this is not an in-depth look, but if you want more experience, Bechtel Innovation Design Center will help you with that. And then I don't have my contact info on the slides. I can have ASME send that out. I disappear in 3 weeks, so 4 weeks or something like that. But this is my email. This pen's.
If you guys want to learn TNT, I would teach you all day. 6-hour workshop. Let's go.
It takes 6-hour workshops.
Honestly, yeah, I went, no joke, went to a 6-hour, 4-hour workshop about tapping, which followed a 3-hour workshop about drilling. Oh no, I don't do it. So.